The photoelectric effect. The photoelectric current. When light is incident on a metal plate, electrons can be caused to be emitted from its surface. This effect can be measured by observing the corresponding electric current and is known as the photoelectric current. It's not as simple as that. We actually see that red light won't produce a current, but green and blue will on a particular metal. If we think of light as a classical wave, then it should not matter what colour it is for photoelectric emission to occur. Provided the light is bright enough and there is enough energy incident on the metal, then we should observe photoelectric emission. As we saw just then, we don't. It matters what colour the light is. It matters what colour photons are incident on the plate. Now that's because different photons, or different colours of light, will have different amounts of energy, as identified by Max Planck. So the energy of a photon is defined as Planck's constant multiplied by the frequency of the radiation. Here everything's being done in joules, but there are equivalent ways of calculating using electron volts, and in fact pretty much any other type of energy. So photons and energy. As was suggested by Max Planck, light comes in packets or quanta, hence quantum mechanics, known as photons. These photons transfer different amounts of energy depending on the frequency of light they represent. The higher the frequency, the bigger the photon of energy. Now, big here we're not using in terms of physical sort of dimensions, we're just sort of saying the amount of energy contained within each packet or in each photon. So red light, low energy photons, low frequency, so they're small. Blue light, high energy, high frequency, so quite big. Now if you compare a 100 watt red lamp to a 100 watt blue lamp, they'll both transfer energy at the same rate because they've got the same power rating, but the red one will emit more photons per second than the blue one does because the red photons are smaller packets of energy. Right, so we'll look at photon color and electron emission for potassium as a particular example. Now, they'll be different for different metals, but with potassium, here the light is described in terms of the wavelength, but it's just the other way around, isn't it? We just use speed is frequency times wavelength to calculate between the two. So 700 nanometers is our lowest frequency, longest wavelength red light. 550 nanometers is the green and 400 nanometers is the blue. And you can see that we have red, small packets of energy, no electrons, green and blue, slightly bigger packets of energy, and electrons are being emitted. So there is a line in the sand, as it were. So there is a specific frequency for each metal that dictates whether photoelectric emission occurs or not. And we call that the threshold frequency. Below the threshold frequency, you won't get any photoelectric emission. So in the case of red light, above it, you do get photoelectric emission, as in the case of green and blue. So red, no electrons, green and blue. Corresponding to the frequency, threshold frequency is the work function, and this has a particular definition, and it's the energy required to just release an electron from the surface of the metal. We're only talking about surface electrons because those are the ones that are most loosely bound to the metal. If you're considering a inner shell or a conduction electron that are deeper in the metal, they're going to require a lot more energy to be released because there's a greater electricity atoms. Right, the work function is related to the threshold frequency using the same equation as we did for photon energy, E equals hf. We're using the Greek letter phi, capital Phi, for work function, which is just a circle with a diagonal dash through it, and that's equal to Planck's constant multiplied by Ft, the threshold frequency. And again, you can interchange between joules or electron volts, depending on which constant you use. Now, bouncers, nightclubs, this obviously, they operate a one in, one out policy, and photons and electrons in the photoelectric effect behave in the same way. The photon is a discrete single entity. It only has the capacity to interact with one electron at a time, just like a bouncer in a nightclub. It will either have enough energy to liberate an electron or it will not. And any excess energy above the work function will be converted into the kinetic energy of the photoelectron that gets emitted. So if you look back at the diagram, you should see that the blue electrons, the blue light that caused electrons to be emitted, have a much greater kinetic energy than the green ones do. So if we look at intensity and kinetic energy, as one photon can only interact with one electron, the intensity of radiation is irrelevant to the kinetic energy of the emitted electrons. So if you've got green light and electrons being emitted, it doesn't matter how bright you make that light, the electrons that are coming off will have the same kinetic energy. I mean, there will be a distribution depending on what the different speeds of the electrons are before they were hit, but we'll ignore that for the time being. Now, either each individual photon has enough energy or it doesn't. Now, increasing the intensity just increases the number of incident photons. It doesn't change. Green light has, 500, however many electron volt energy packets. It doesn't, making it brighter just increases the number of packets, not the size of them. However, if you increase the intensity, you will increase the photoelectric current. Because each photon causes an electron to be emitted, so therefore if I have more photons per second, I get more electrons per second, which corresponds to an increase in. So back to the diagram again, now with some values on it. You can see red light, 1.77 electron volt photon packets. Green light, 2.25 electron volt photons. And blue light, 3.1 electron volts. So you can see that the green causes electrons to be emitted. The blue causes electrons to be emitted, but they've got an even greater kinetic energy afterwards. And the red light just might warm the plate up a little bit or get reflected. It's not being absorbed by photoelectric effect. Right, the photoelectric equation then, this is just a statement of the conservation of energy. If HF represents the incident photon, phi represents the work done against the metal in order to liberate the electron, then EK is the remaining kinetic energy of any emitted photoelectron. Now, if you are going to jump around between joules and electron volts, which quite often exam questions like to do, then you will need to be careful that you have got the right value for Planck's constant that's appropriate to the units that you're working in. It doesn't matter which units you work in, as long as you're consistent. So either convert it all at the beginning or convert it at the end, but don't start messing around in the Here we have the gold leaf electroscope, which is a neat little way of demonstrating the photoelectric effect in action. You have a metal disc connected to a gold leaf and a metal plate inside an evacuated box. Now, if that metal disc is made of zinc, for example, and ultraviolet light is incident on it, then electrons can be caused to be emitted by the process of the photoelectric effect. That then means that the gold leaf and the metal plate within the box, along with the metal disc itself, will become positively charged because they have lost electrons. As a result, the gold leaf, which is free to move, is now positive, as is the metal plate. They repel each other, and the gold leaf will rise up, as is shown. If you earth the metal disc and return the electrons to the system, then everything earths, and the gold leaf will fall back down again to its original position. And here's just a brief summary from the exam board syllabus stating exactly what can and cannot be in the exam.